Computing probability of type 2 errors and power. In this demonstration, we shall consider normal distributions and averages. This slideshow demonstrates how to compute the probability of type 2 errors and the power of a statistical test through examples. The null hypothesis considered is mu equal to mu naught. Each of the three possible alternate hypotheses are considered. For our first example, we'll consider a left-sided test. Suppose we wish to test the following. The null hypothesis is that the population average is equal to 20. The alternate hypothesis is that the population average is less than 20. We have an alpha level of 0.025, a population standard deviation of 3, and a sample size of 18. This is a left-sided or left-tail test. The normal curve we draw should be normal, centered at 20, with 3 divided by the square root of 18 as the distribution curve. And we simplified here by saying that it is normal, centered at 20, with square root of 2 divided by 2 as the standard deviation for this particular curve. Suppose we feel that the true average is actually 19. The first step in determining type 2 errors is to draw the normal density curve as provided. Normal centered at mu with a standard deviation of sigma over square root n. So we'll draw a normal density centered at the claimed value, but the standard deviation is from the sampling distribution of the means. And here is a diagram for this particular example. Here we see that the claim is at 20. We are centered at 20, and we have the standard deviation measured appropriately. The second step is that we're going to determine where the cutoff value would be to make a type 1 error. So we find out where we need to cut the normal density curve in order to have an area of alpha to the left of the slice. And that is shown here. For our calculations, the cutoff score would be about 18.614. So for this particular normal density, the area shaded in red here is equal to alpha, that's 0.025. We draw a new normal density curve in step 3. This new normal density will be centered at the new value, but it will have the same standard deviation as the original curve, sigma over square root n. The new center is at the alternate claim, and the standard deviation will be the same for both of these curves. After drawing the new normal density curve from the cutoff value found in step 2, compute the area under the new normal density to the right of that cutoff value. In the next picture, the blue curve is the new density curve, the red curve is the old density curve. Beta, the probability of a type 2 error, will be shaded in blue on this next diagram. So here is the diagram described previously. Notice that the region in blue is shaded under the new curve, but it starts at the slice where the old curve was, and it is in the other direction from alpha. Okay? This represents the values that we would believe to be indistinguishable between 19 and 20. And what I mean by that is if we got an average of 19.5, then we would have evidence to support the claim that the true average was 20. But we would in fact be incorrect because the true average was 19. And we would not be able to tell the difference between those two results based on a sample of like 19.5. So this blue shaded area represents the probability of a type 2 error. the probability of failing to reject a claim that is indeed false. So if 19 were the true average, and we thought it was 20, and we saw a sample whose average was 19.5, we would not reject the claim that the average was 20, and we would be incorrect to do so, because it would be in this blue region. Since the power may be considered the probability of making the correct decision to reject the null hypothesis when it is indeed false, we simply take 1 minus beta to compute the power. So the power of our test, in our first example, is about 0.4088. And that's about 40% power. To interpret these results, this is how to do it. The probability of rejecting H0 when it is in fact true is 2.5%, or 0.025. This is a type 1 error. This is the same as alpha. The probability of failing to reject H0 when it is in fact false is about 0.5912, or about 59%. And this is a type 2 error. The probability of correctly rejecting the null hypothesis in favor of the alternate claim when the null hypothesis is in fact false, in this example, is only about 0.4088, or about 41%. And that is the power of the test. Let's look at another example for a right-sided test this time. Suppose we are researching whether or not the average age of a mother is now older when she has her first child than it was in 1990. Data obtained from the National Vital Statistics Report, volume 48, number 14, suggests the average age in 1990 for first-time mothers was 26.4 years old. Suppose we obtain a random sample of 50 first-time mothers. Assume the standard deviation for this population is 6.4 years. Suppose this researcher believes the new average age is actually 27 years old and is using an alpha of 0.025. Our problem will be deciphered as follows. The claim is 26.4 for the null hypothesis. In other words, there is no change from first-time mothers back in the 90s as opposed to presently. Our alternate is that the average has increased. It's greater than 26.4. The alternate claim is that the new average age is 27, and this is going to help us determine the type 2 error and the power based on this alternate claim. The alpha level is 0.025. The sample size is 50, and the standard deviation for the population is 6.4. Our first step, we draw the normal density curve. Normal centered at the claimed value for the test, the null hypothesis claim, with a standard deviation of sigma over square root n. So we draw a normal density whose center is at the claimed value, but the standard deviation is from the sampling distribution of the means. So here is our picture. The normal density is centered at 26.4, and we have our standard deviation. Next, we determine where the cutoff value would be to make a type 1 error. So we find out where we need to cut the normal density curve in order to have an area of alpha to the right of that slice. So here is our diagram. Our cutoff value is computed at 28.174, and the area to the right of that under this particular normal density is 0.025, or 2.5%. So we're going to draw a new normal density curve centered at the new alternate claim with the same standard deviation from the sampling distributions that we had before. And this is how you start step 3. So the new center is at the alternate claim, standard deviation is the same for both curves. After drawing the new normal density curve, from the cutoff value found in step 2, compute the area under the new normal density to the left of the cutoff value. In the next picture, the blue curve is the new density curve and the red curve is the old density curve. And beta, the probability of a type 2 error, will be shaded in blue. So here is our picture. We can see the original curve here in red, and we see that we have that slice where that alpha starts and then goes to the right. We have a new curve centered at 27, that's in blue. That is the new curve that would suit the alternate claim that the researcher thinks that the average age is now 27. From that slice, that black vertical line, shade to the left. In this region, we would not be able to reject an incorrect or inaccurate claim if 27 is actually correct. We would not be able to distinguish between the 26.4 and the 27. So any results that occur in the blue shaded region, we would not be able to say that the old claim at 26.4 is no longer correct, and that is a type 2 error. Since the power may be considered the probability of making the correct decision to reject the null hypothesis when it is indeed false, we simply take 1 minus beta. So the power of our test in our example is about 0.1631. So let's interpret these results. The probability of rejecting the null hypothesis when it is in fact true is 0.025. That is a type 1 error. The probability of failing to reject H0 when it is in fact false is 0.8369. This is a type 2 error. And the probability of rejecting H0 in favor of the alternate claim when H0 is in fact false is 0.1631. That is the power of the test. For our third example, we will consider a two-tailed test. Suppose we have the following test. Someone claims that the population average is 45. The alternate claim is that it is different from 45, or not equal to 45. Let's say that someone believes it to be 46.5 instead. This time we'll use an alpha level of 0.05, a sample size of 40 with a population standard deviation of 8. Step 1 again, first draw the normal density curve with the curve centered at the claimed value, and again the standard deviation is from the sampling distribution of the means. In other words, it's from the population standard deviation divided by square root of the sample size. So here is our diagram to start us off. This particular curve is centered at 45 and has the appropriate standard deviation from the sampling distribution of the means. Step 2 again, we determine where the cutoff values would be in order to make a type 1 error. So we find out where we need to cut the normal density curve in order to have an area of alpha over 2 to the left and to the right of these slices. Remember, the total area should be alpha, and symmetry of the normal density curve allows us to use alpha over 2 for a two-tailed test. So here we have our cutoff values at 42.52 and at 47.48. The areas shaded in red are both 2.5% of the area under the curve entirely. So when you add them up, you get 5%, and that was our alpha level. Step 3, again, we draw a new normal density curve centered at the alternate claim. In this example, 46.5. But we use the same standard deviation. So that does not change. We have a new center, but same standard deviation for both curves. And after drawing the new normal density from the cutoff values found in step 2, compute the area under the new normal density that is between the cutoff values this time. And in the next picture, the blue curve again will be the new density curve. The red curve is the old density curve. And again, beta will be shaded in blue. So here we have our new curve in blue centered at the claimed value at 46.5. The shading starts at the slice for one of the cutoffs, and it stops at the other slice for the cutoff. So if you're reading from left to right, the shading under the curve will start at 42.47 and it stops at 47.48, and we need to compute the area under the new normal density for this amount of area. The reason why this is the case is because in one of these red regions, this is what we are calling a rare result if the old claim is true. So if we get a sample average that falls in these two red regions, in one of these two red regions, then we will reject the claim. And remember that beta is the probability of failing to reject the claim. So it has to be under the new curve, but not sharing the same shading or the same shaded region as what is shaded in red from the old curve. And I know that sounds like a lot, but just remember what beta means. Beta is the probability of failing to reject a claim that is inaccurate. So if the claim of 45 is inaccurate between 42.47 and 47.48 under the new curve where we think the new average would be, if we get a sample average that's between those two cutoff scores, we will not be able to tell the difference between the new claim and the old claim, and that is why we would make a type 2 error, because we would fail to reject. This is in the region of what we would consider to be commonplace for the old curve. Since the power may be considered the probability of making the correct decision to reject the null hypothesis when it is indeed false, we simply take 1 minus beta to compute it. So the power for our test in our example is about 0.2203. Let's interpret these results. The probability of rejecting the claim when it is in fact true is 0.05. That is a type 1 error. The probability of failing to reject H0 when it is in fact false is about 0.7797. That is a type 2 error. That's the blue regions in our graphs. The probability of rejecting the null hypothesis in favor of the alternate claim when the null hypothesis is in fact false is about 0.2203, and that is the power of the test. The probability of making the correct decision based on the evidence. Thank you for your time and attention.